Okay, today I'm going to solve another problem, which I think it's really cool to solve. It's called generate parentheses. It's a medium difficulty problem. And it's asked a lot by Amazon in the last 6 months. We don't have Adobe, Google, Uber, Apple, Facebook, Microsoft, Bloomberg. But of course, the company that has asked it most time during DSA rounds is Amazon. Okay. So we will, solve this in two ways. There's two ways that I'm going to show how to solve it. There's one way that it's not so optimal, but nonetheless, it's good to show. And then there's another way that is more optimal because it doesn't explore like so much the search space. Okay, so the problem statement is also very short, which I love. So it reads like this: given n pairs of parentheses, write a function to generate all combinations of well-formed parentheses. So generate all combinations. So typically when a problem asks to generate all possible combinations or find all the possible ways or enumerate all the maximum numbers, for example, and all of this stuff, like find as many things as possible or all constraints that meet such criteria. They're basically combinatorial problems as well, or for example, counting problems as well. But in this case, of course, it's a combinatorial problem. We need to find all the combinations of parentheses, of well-formed parentheses, right? So in this case, for example, here the input is 3. So we have 3 pairs of parentheses, and then here are all the possible valid combinations. So we have 3 adjacent parentheses, and then, for example, here we have a parent parentheses and 2 child ones that are nested. This one is just a single parent and then 2 nested child parentheses. And then this one is 1 parenthesis, and of course we can only generate this combination here. Also, the constraints are extremely small, and usually this is the case for these types of problems. So what this means is that the time complexity wouldn't really matter so much, just because of the constraints are quite flexible. So let's walk through those 2 different solutions. So I'm going to use an n equals 2 to do that because it's more manageable to diagram than this. So let's do here an n equals 2, and the expected combinations of parentheses. So we have this, so 2 adjacent ones, and then of course 1 nested one, right? And then there's a bunch of invalid ones that we're gonna see, invalid combinations. So just to get things started, like with the logic, is that this one here, so a parenthesis basically is obviously composed of 1 opening character and 1 closed character, right? Then the other thing to note, like another property, basically, another property is the length in this case of this group, right? So the length is 4, right? So we have 4 parentheses characters, 1, 2, 3, and 4, right? So basically, the length can be generalized of one of these groups as 2n, right? And of course, since n is 2, it will be 2 times 2, right? And then that will equal 4. So that's like another property. Another property that's also worth mentioning is that we have always, in this case, 2 pairs of opening parentheses and then 2 pairs of closing parentheses. And that's going to be the basis for doing the validation check. And all of these properties will work independently, like in the first version of the solution or in the more optimal one. Okay, cool. And then of course we will only validate once we reach 2n, right? So if the P group is valid, sorry, if P group length equals 2n, then we validate it, right? So that's another thing. And then of course, if it's valid, we need to add it to a collection, right? So the other important thing is if P group is valid, add to result array. And that again works like the global, let's say the core of the logic for both solutions. So I'm going to walk through or outline like the computational tree of the first solution. Okay, so let's start. I'm gonna start here with an empty string. So what's gonna happen is that at each iteration, right? So we're gonna have like some kind of while loop, some kind of loop that at each iteration we're gonna build this group, right? Like these group of parentheses, right? So at each iteration we will always have two options, like either add an opening parentheses character or a closing parentheses character. So immediately this could be basically represented like this. You can have this thing here, and then I'm gonna copy this one, and then of course this will become an opening, and then this one will become a closed one. Okay. And then after that, of course, we have space here, just in case there's more space needed. Then of course, from here, we have the same logic. So at this step, we also have two options, right? So with this one, we will add another opening one. And then in the right subtree, we're gonna add a closing one, right? And then here will be the same. So to this one, this is gonna be an opening one. And then here, instead of an opening one, is gonna be a closed one, right? Okay, cool. So we can continue basically this iteration. And I mean, this layout, of course, it's like looking kind of like or not kind of, it is a binary tree, right? And it's just because we simply have two options, two paths to explore at each iteration. So it's similar. Okay, get rid of this thing. Okay, right? So, oh my God. So it's similar to, so for example, again, the famous Fibonacci thing shown in previous videos. So it's similar to this Fibonacci sequence, right? It's like, again, like a binary tree. And again, it's because, like, for example, here in this mathematical definition of the Fibonacci, how to compute the Fibonacci sequence, at each iteration, we're like recursively calling the same function, right? So that's why it branches out. Like the number of branches depends on the number of times a recursive method is calling itself, right? So if it's calling itself 5 times, well, we will have 5 possible, well, it will not be a binary tree there, it will be another type of tree. We'll have like 5 branches, 5 possibilities, 5 paths to explore at each iteration. So let's continue drawing this. So we're gonna have this here, this one here, this one here. I'm kind of running out of space. Okay, so this one will be, again, another opening one. And then here we will have one closing one. And then this one here, we will have an opening one. And then here we will have a closing one. So here, right, we're starting to like see like these guys are starting to emerge. And then we're gonna do another depth, right? So let's just make this one like this. And then this one like this. Okay. So here, of course, like this will keep here, right? So reach the end. So this is 2n. And then this one, we'll have this closing one. And then this one here, we'll have a, sorry, an opening one. And then this one here will have a closing one. So now we found this one, right, over here. And then here, this one, so this one will have an opening one here, and then this one will have a closing one, right? So we already found the other valid pair. And let's just complete this section here. So this one will have an opening one, and then this one will have a closing one, right? So then we can immediately see, like just they're diagramming this this computation for n equals 2 is like we found one of the valid ones right here and here. So of course, when we're like running the validate function, it will basically like this will be valid, right? And then we will add it to our like result array. But then we also have like a bunch of invalid ones, right? Like this is invalid, this is invalid, this is invalid. All of these guys here, this one is invalid, right? Well, sorry, I'm getting ahead of myself. This one, it will not even be validated. Only these leaf nodes. But then we also see, for example, that this didn't really need to be explored as well. So like all of this basically path is invalid. And of course, I didn't keep just drawing it here, although I could have. But you know, this whole subtree basically will basically be you know, containing invalid will contain invalid parenthesis groups. Well, this one will of course contain some invalid ones, but at the end we'll arrive like at the result that we want. So in terms of the time and space complexity of this, so we will have so it's time complexity, so it will be big O of 2 to the power of 2n, right? And of course, it's 2 because we have these two possibilities to the power of 2n. We can see it here, like at each iteration, we will want to generate a string of 2n, right? So that's why it's exponential. Like, I mean, we graphically can see it here. It like will grow exponentially, this tree, as the tree, of course, as the levels increase. And then, of course, times n. And times n is because with the validate function, like we would have to iterate through all of these pairs. And then, of course, it's, sorry, not, well, I actually simplified it beforehand. So it's times 2n, right? Because we have to iterate through all these pairs, which, of course, will be the length of 2n. But then this could be further simplified to 4 to the power of n times n. And then the space complexity of this solution would be the same as well, because we're storing all of this basically results. Okay. Okay, perfect. And then the other, sorry, not times n, it would be 4n, because like we're not taking into account this. So this is just the, you know, the overall memory that is needed. So let me remove this. because of course we're not going to store anything while we're doing the validation. So it's 4 to the n, right? And what does this mean? That if we just take, 4 to the n, so basically, so all possible combinations are 4 to the n, right? Oops. 4 to the n, which basically in this case is 4 to the power of 2. And then that will be 16, right? So we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sorry. 4 possible combinations, but of length 4, right? So then we will have 1, 2, 3, 4, 5, 6, 7, 8, right? So we have 8 here because we drew it. And then of course we will have this one. So it will be a total of all possible combinations of parentheses which are or parentheses groups which have length 2n, right? So that will basically be yeah, that will be that. So of course that will equal 16, right? Because we cannot see the other part here because I didn't draw it. So that's all the possible combinations. We're gonna store all of these things right now in memory, of course, but there's lots of them that we don't need to store, right? We only need to care about like these two, right? So that's the inefficiencies of this approach, so to speak. But let's anyhow just implement it, because I think it's just a good exercise to demonstrate why not. So let's go ahead and start this thing. Okay, so we need our result, right? So our something to store the result, like this output. So we are gonna say we can name it valid combinations, and of course it's gonna be a list of strings. And then we can have like a stack, although this could also be implemented with a queue. So I'm gonna leave this here. Queuing can also work. The queue can also work because in this case we doesn't really matter the order in which we produce these groups. Okay, so and then we can say we can do this while loop. So while the stack is not empty, right? So at the end of the day, for example, like this stack, once these two groups have been added here and we're finished like exploring all the space, it will be left with mostly all invalid parentheses groups, and then that's when basically where it's gonna be, everything is gonna be popped, and then the while loop of course will exit. So we can say current yeah, let's say current group. We can say p group, and then stack that we pop it from the stack, and then here of course we will initialize it with an empty string. So of course in the first iteration this will be the empty string here. And then of course we need our base condition to when to check, right? So this, if the length is 2n, then we validate it. So it's if the length of this, like we're checking the number of characters, so the number of characters equals 2 times n, we then validate, right? So we need to have some function here that says there validate. And then we're gonna take our current parentheses group here. Perfect. So let's for a moment pass this. So self validate, and of course this should return a boolean, a true, and then we pass in this guy, and if it is valid, we of course add this thing to our results, to our valid combination current p group. Okay, so cool, and then we ignore the rest of the iteration. Awesome. So let's write this validate thing really quick. So there's several cases we need to take care of. So for example, let's still stick with when n equals 2 for the rest of this this example here, n equals 2. So we know like this is a valid one. Then we know that this is another valid one, right? Well, I'm giving myself actually, let's just be consistent. This is another valid, right? And then we also need to account here for some edge conditions. So for example, if we have something like this has the properties we discussed about. So for example, two opening characters here and then two closing ones. But then clearly we can see like this is not valid, right? This is not a valid parenthesis. Right? So it's not invalid. So we need to account for that. So the first thing that we need to do is we need to have like some counter, right? So we're gonna have a counter for opening parentheses count, right? For these guys. And then we are gonna loop, as we said, through all of this. So P group, and then we're gonna see, okay, if this character is an open parentheses character, well, let's name this as open, better, open, shorter. Then we increment that count. Run it again by mistake. Anyway, we increment this count, right? Opening P count plus equals 1. And then the other thing is, like, if it's a closing one, if it's a closing character, of course, like we can, oh shit, stupid short key. We can decrement it by 1. And then of course, like what we want at the end is that this is 0, right? Like this, right? Like this will be 0 because we have two, like, right? Two opening and two closed. So for example, the first one will be open. So it will add 1. So this will be 1, and then will be a closed character next. So it will decrement the count. So now it will be 0. And then this encounters again an opening 1. So it will increment it to 1. And then it encounters a closing 1. It decrements it by 1. So this should be 0 again. And of course, if it's 0, it will be valid. But not in this case, right? Because in this case, our current implementation here will also return true for this. So there's another check we need to do. So if immediately we have an opening count which is smaller than 0, we return false. And this is also very important because to have a valid parenthesis, the first character has to be an opening character. And of course, like that's another important property. The first character has to be an opening character, right? So in this case, this parenthesis group, the first character is a closing character. So immediately this will be opening count will be -1. And then after that, we will return false, right? So this handles this edge case. So, okay, cool. So let's continue. And then we are going to start, of course, since we're through each iteration, again, we have two of these possibilities, adding opening or closing. Well, we are going to do that right now. So to this, we will say stack.append current P group plus the opening and the closing one. So that's basically here building this, right? So this one, and then on the current one, of course, this is the current one in this case. So we were adding an opening one, and then here we're adding a closing one, and so forth. And then at the end, we can simply return our valid combinations. And yeah, so let's run the first test cases. So they're all accepted, as we can see. And then we can generate all the test cases right now as well. So it's 2, 8. So we have 2, 4, 5, 6, 7, and 8. So let's run all of them. And yep, they all pass. So for example, like if we go to input is 8, like we have all of these groups, right? All of these possible groups. Of course, it's truncated. So yeah, and then for example, if we have n equals 4, we have all of these possible combinations. Anyway, so let's now, I'm gonna comment this out. I'm gonna comment this one out, and let's go for the other one, which is the more optimal one. So let me take this here and come here. And then also let's take this thing here, well, to have it as reference. So this one is basically we're gonna use we're gonna evaluate if the current parenthesis group is valid, and if it is, like we're gonna keep basically constructing that parenthesis group. So we're not gonna explore branches which are invalid. So in this solution, for example, we will not even look at this, right? Or we will not even like explore this part either. So it will be much more efficient. So the way this is going to be done is the following. I'm going to draw it out again. And then this approach will also use backtracking to always like go back to the previously known valid group to build from. So I'm gonna illustrate this as well, so we can also compare it from this one. So we're gonna use again n equals 2. So so here, for example, we will start with an opening character, and let's draw this out here. And then here, did I say? Okay, I chose here this one. Okay, fine. Yeah, doesn't matter. So here will be a closing. And then here we will have an opening one. Another opening one, right? And then we do the same. Without. Okay, so one thing here is that we will basically do this validation here in place. So basically the condition is so we will need some variables, right? So this is going to be, we're going to implement this recursively. So we're going to need some variables that we can steal the name actually from here. For example, if open parentheses count is smaller than our n, add our thing, right? Our opening character to the existing group. And then the other condition is if closed parentheses count is smaller than the open parentheses count, we will add the closed one, right? We will add the closed one. So this is the check we're gonna do now. So for example, here, this one, we have 2 opening ones, right? So, and then of course, we can only add another opening one if the current opening count is less than n, but here is not less than n, is equal. So immediately, like this branch here wouldn't even be explored, right? We will only add a closing parenthesis to this one. And this, we will do the same check. Okay, we have one opening and one closing. So we can explore the two branches. So here we will have the opening one. And then here we will have the closing one, right? We'll have the closing one. So let's now go down this path. So this path, we'll have this here, this thing here, and then this will be an opening one, right? Here, and then here we will have a closing one, right? Okay, so this, of course, we found already a valid pair here. And then this, actually, wait, this wouldn't even be explored. So let me just remove it here. Again, why? Because we already have two opening ones. And then again, we can only add another opening character if the opening character count is below n. But right now, like it's equal, right? So then this path will basically not be explored. This path will not be explored here, right? And then here we have arrived at a valid answer. So, okay, the length is 2n. So then we will add it to our result, right? So then let's continue with this. So this one, we have one opening, right? Sorry, we have two opening ones. So then immediately this, we will not explore this path. So if we draw this one, this will not be explored, but we have this guy here to explore. So we only have one opening. Sorry, we only have one closing one, right? So, and two openings. So of course, this condition will hold true because our close count is 1 and our opening count is 2. So close count is smaller than opening count. So we have this guy now, right? Phase that out. Okay, cool. So now we have find the other one, right? We found the other one here. Oops, that's okay. We have this one, right? And now we, of course, we have here, for example, two opening ones. Sorry, two closed ones, right? But we have two closed and one opening. So the only path we could potentially explore. Oh, wait a minute. I think, let me see if I made a mistake. This one here. Yeah, so wait a minute. This looks correct. So we have a closing one. And then here also closing one. So this one and this one. And then this one is also a closing one. Yeah, so okay, let's just draw this one just clearly, because this one will also could not be represented. This one I just draw it more clearly, not be explored, because in this case we will need to add an opening one here, for example. And in this case, this will be like a closed one, right? But then here, we would have this one here, and then this one, two closing ones. This one will not even be explored, right? Because we cannot add, because right now we have two closing ones and one opening one, right? And then our condition is to be closed one. The closed parenthesis has to be less than the opening one. So this wouldn't even be explored. And then in this one, we will add, of course, we'll have these two here, and then this opening one here. So it will still be basically invalid, right? So we will only add, this will be the final result. So as we can see, this tree, this right, this space, or this search space, it's much more efficient than this one. And you can imagine, like, once the n scales, well, those are huge trees. But we're only exploring like valid parts, like valid subtrees, right? And we don't explore branches which we know are invalid. So that's the whole idea with this other approach. So if I come here, so in terms of the space complexity, can remove this. This in time complexity, it's more kind of more tricky to derive it, but it's we have to divide it by it's some kind of I mean, since we're reducing the search space, it's going to be divided by some kind of expression, which represents like this reduction in space. So I'm just going to leave it at x for now, and then it's going to be the same. It's going to be the same for here, so as memory, because we're basically only, so here, since it's going to be recursive, it could be more complicated here. So we have 1 depth, 2 depth, so we have 1, 2, 3. Yeah, this one, the space complexity could be more complicated, but I think it could also be represented by this. Yeah, it could also actually be represented by this, because we're still in these iterations. So it will still be the same, because our call stack will contain the same amount of iterations as this tree, basically. Okay, so yeah, this should be the same space complexity value as well, divided by some expression. Okay, so let's implement this one. And then for that, we're gonna need a function. So we can say generate valid combinations. And for that, we will need a result string. We can like reuse this naming. Let's reuse this, guys. So we will need a current, let's call it current parentheses, or current, let's recycle names, current pre-group. Then we are going to come here, recycle. We're going to say the open parentheses count. Then we're going to have this one closed parentheses count. And then we're going to pass in the n, right? N into this function. And then we are going to have our base case, right? So this is a recursive function. All recursive functions need to have a base case, so we don't end up in an infinite loop. So our base case is going to be if the length of our current P group equals 2 times n, right? It's very similar to this. We will add, as we already know, this one is valid. We will add this thing, right, to our valid combinations, and then we will return, right? That's going to be the base case. And then we can take these guys here, these conditions. So if open count is smaller than n, we can call this thing here. Call here, call itself, and we of course are going to pass we are going to pass our this thing here, our current P group, and then to that we will add an opening parentheses. An opening parentheses. We will increment this count by 1, and the close count will be just left untouched, and then we will pass the n. And we can do the same for this. So let's copy this thing here. So we will add the closing. This will be left untouched. We will increment the closing by 1, and that should be it. So let's call this here the main function. So valid combinations, let's just reuse this guy. So we say valid combinations, and then our current parentheses group, we can just pass an empty string as well. And then here we have, of course, it will be 0, no opening parentheses, no close parentheses, and then we pass the n. And then when this returns, we will give the result. Okay, so let's walk through this. Let's do a little dry run of this using the diagram. So we have this first one, right? That's added, and then after that, this calls itself, and now we're here. And of course, we only have 1 character, so this condition is not met. And then we only have 1 open character. We don't have 2 open characters, so this function will call itself again, right? So this one will be the parentheses group now. And then after that, we are gonna do the same evaluation. So we have now open parentheses count is 2, right? So this condition will be false. So now we will go and explore the right subtree, right? So the closed parentheses count is 0, which is smaller than 2, right? So then we will append a closing one, right? So it's here, we append the closing one, right? And then after that, so here, this one has already been visited, this one has already been visited. And then after that, we're gonna do the same check. So we have, this will not come into place because we have 3 characters. Opening parentheses count is already 2. So we'll add another closing one, right? So this will call itself once more, and we will arrive at this one, right? So now this will call itself when this, then inside the next level will be here, right? Which is here. And then it says, okay, yes, the group has 4 characters to n, and we'll add it to our results, or valid combinations, and then we will return, right? And once we return, of course, this will be popped up the stack, the call stack, the internal call stack, right? So then this thing will be basically popped, right? And then we will come here. And then after that, this will also come here again, and this will be popped, right? Once more. And then now we will be here, which is here, right? And then this will be popped once again, and then we will be here, right? And after that, we will basically be here, right? Here's our color, and then of course, our open parentheses count is 1, right? And now, and our closed parentheses count is 0, right? Because we don't have any closed parentheses count. And now we're gonna explore all the right subtree, right? All of this side is gonna be explored. And then we do the same thing, right? So we come here, and then this is added, right? So we add a closing one. So now we are here, and the cycle repeats itself, right? Until it finds this guy, and then it returns, and then everything starts to, of course, pop from the stack. This starts to pop from the stack. This pops from the stack. This pops from the stack, and then this pops from the stack, and then this returns. Finally, we returns, and then we're here, and then we already explored all the possible combinations, and then we return the result. So hopefully, like if we run all of this, everything should work. And yes, everything worked perfectly. So that's it. I mean, let's just submit it. Again, I mean, this one I previously solved it, but this video is like a walkthrough of the logic and the thought process of how the solution works. So let's just submit it. And then here it is. Yeah, these metrics don't really matter, but for the sake of it, let's just run it again so it stabilizes itself. Yeah, cool. Okay, anyway. Okay, cool. So this is the logic for this one. So this is the end of the video, and I hope, I mean, all of this diagrammatic, like high-level computations of the both algorithms was clear.